All right, hello everyone. Welcome back to Historical Geology 1404. Today is lecture 4, the last lecture of module 1. According to our syllabus schedule, that means that on Wednesday, 2 days from now, we will have our exam 1 review and exam 1 will open. You'll also be getting lab 2. No, I already gave you lab 2. What am I talking about? We did it last week. What else? I think that's it. So this is the last reminder to my online students that you will need to get me your questions for that exam review no later than tomorrow night. That will be Tuesday the 31st. There are 31 days in March, right? Yes, okay. Yes, okay. Tuesday the 31st. You need to get me your questions for the exam review recording no later than that. Can't think of any other announcements. Any questions or cool things to talk about? No? Yeah, Artemis II launch coming up. 2 days from now is the anticipated launch day, April 1st. Hopefully it won't be a joke. It would be a very expensive joke. So far, I haven't gotten any news alerts today saying that it's failed any tests. So I think everything is going well so far. Fingers crossed. On that note, I mentioned to you guys last week that, and I for those of you that were here in person, I showed you the recording of Jared Isaacman, the director of NASA, giving that big presentation and saying, hey, these are the objectives for NASA in the next 7 years, right? Very, very, very cool. And one of those objectives was in the next year and a half, they are launching the first ever nuclear-powered Starship to Mars to deliver a fleet of copters to start surveying the landscape better. Well, I attended a virtual space technology symposium on Friday morning, and one of the most interesting presentations was about how they are making these nuclear thermal engines. Okay, so the trickiest thing with nuclear technology is how dangerous it can be. Now, here on Earth, we have quite a lot of infrastructure built into containing how dangerous those things can be. If you've ever seen a nuclear reactor facility, it's massive. It covers acres, okay? Acres of property, and all of that is tied into not only the reactor itself, but all of the protective systems, the fail-safes for those protection systems, and the fail-safes for those fail-safes, okay? There's a lot of infrastructure that goes into that because human response time to an emergency sometimes lacks. A lot of the times when we've had one of these nuclear disasters, it's because of a natural disaster that we couldn't foresee or human error, okay? And so there's an interesting way that they were talking about in this presentation for how they get past that when we're talking about building a nuclear-powered spaceship. If you don't have a human there to monitor it, and even with a human, you know, a human's response time for an alert to go off, for the human to realize what it is and to take an action might be a second or two, right? Even the fastest human response time is probably a second and a half, right? So the answer then is some way to make the issues, the potential problems with the nuclear reactor not more predictable, but the response to them more instantaneous. So you can scale down the size of your nuclear operation, less protective measures, if you are more certain that the initial measure will actually happen. How do you do that? How do you do something instantaneously? Well, the answer these days is you train an AI how to do it. So that's what they're doing. They have taken this machine learning software, which is, you know, code speak for an AI, okay? And they are teaching it how to recognize every potential issue that could arise with a nuclear-powered engine. And anytime there's a fluctuation, or if you know the neutron cascade is running out of control, or if they need more energy, it will be able to respond to those prompts instantaneously, far, far, far faster than any human or traditional program could before. And while that sounds really cool, they told us as well how they are training the AI to do it. And this was where I began to get a little bit concerned about it. You all know that I think AI is very cool for certain purposes. I don't think that it should or can be used for anything. This was a very cool application of it, but the way that they're training it to do this is a little questionable to me. They're using incentive-based learning. Basically, every time the AI makes a choice in this training regimen it has, and it's the right choice, they give it a reward. It's like giving a kid marshmallows. Good choice, have a marshmallow. Good choice, have a marshmallow. You told the truth, have a marshmallow. Is there a potential problem with this you can think of? I know none of you are parents, but you might have had enough experience with kids to know where I'm going with it.
They're not going to do nothing.
Huh?
They're only going to do things because of the incentive. And once they get the incentive, they're not going to do it.
That's true. They will focus on the incentive rather than achieving the objective itself. That is one aspect, not the main one I could think of.
Did you hear about, I forgot the name of the company, the U.S. government wanted to buy like, the rights to make a fully automatic weapon that was trained by AI, but the company didn't want to sell like the rights because they didn't think it was ethical for there to be like a machine making the decision of whether they should take someone's life or not.
Yeah.
And then like that open AI sold or like not sold, but like started helping the U.S. government with like making fully automatic weapons.
I did hear about that. So I'll repeat that for the purpose of the recording here. Alma was talking about how there was a company that the U.S. military approached to make AI-powered weaponry. And the company said, no, we don't think that sort of power should be put into the hands of an AI to take a human life. And the military has started working with another company to develop it. Yes, that is true. And those weapons currently exist. Right now, they are being trained how to destroy drones. Okay? But there is absolutely the intent to have anti-human AI-powered weapons as well. That is in our future. But back to the subject of the nuclear thing, can you see an issue with that? Okay, Jasmine?
They might not do anything unless like they're guaranteed a reward.
That's true. If you have to give a reward every time, but here's the thing. When we're talking about a reward for a computer program, it's a completely like fabricated digital currency, right? Right. If you give it an electric zap, good job, yay! You build essentially a pleasure center into it, and you say, hey, good job. Have a little bit of pleasure. Good job, right? They've done this with rats, actually, where they've put an electrode into a rat's pleasure center, and every time it does a certain thing, they give it a little bit of pleasure, and it learns how to be addicted to that pleasure center. It's the same concept for why humans go back to drugs, why we get addicted to drugs. It hits those pleasure centers, and we train ourselves to need it. Okay? So that is a potential issue. What I'm getting at here is how many children can you think of who, when prompted to do a thing for a reward, like a marshmallow, doesn't end up lying for it? If I told a kid, hey, you go clean your room and I'll give you 10 marshmallows, my kid would do it the first time, probably the second time, but then at some point they would realize, if I just tell Daddy that I cleaned my room, he'll still give me 10 marshmallows. All of my children have reached that phase. Every child that I have ever met in my life eventually realizes they can lie for a reward, and they do it at least once. All well and good. It's a kid. There are no stakes for cleaning their room. They learn a lesson when I decide that the reward gets taken away, or they won't get a reward the next time. But what happens when it's an AI in charge of a nuclear reactor? And it lies to get the reward. That's my main concern here. Now, if we have a way of making sure that it only lies the once, learns its lesson by not receiving the reward, and then decides not to do that again, that's fine. But kids never lie just once. And I think it's dangerous to compare AI to humans too much, but I think it's right now at our current stage of AI development, we should definitely consider their cognitive development to be children. And so I would personally be a little bit questionable about putting something as powerful as an AI reactor that needs to be held at a perfect balance in the hands of a system that has the potential to lie because all it wants is a reward, because that's how it's been trained. Now, there are other AI systems like Claude. Have you guys heard of Claude? Claude is the AI program developed by Anthropic. Anthropic's whole thing is ethical AI. Their main, their I guess you could say, constitution for their AI, the core programming for their AI has things like never ever hurt a human, never ever do anything that could support the hurting of a human, things like that. But also, it will never make up information or anything like that. It's in the core programming. OpenAI's ChatGPT, Twitter's Grok, all of those, they do not have the same core programs. Okay? As far as I'm aware, Claude is the only large language model that has those as part of its core programming, which is why most people don't pick it, because all of those things come at the cost of things like personality, right? Claude doesn't have the same personality. You ask ChatGPT, hey, how do I look in this dress? And it'll say, oh, you look great, that's fantastic. Even if it thinks, logically speaking, like data-driven wise, you don't. It will still compliment you. That's how it's been built. More of a personality, more of a person in there. Like a friend would lie to you. Claude will say, well, according to current fashion standards, you're living in the early 2000s. Right? It will straight up tell you the truth, no matter what your feelings are. Safer, less personable, right? It doesn't care about your feelings. It just cares about expressing true information. So, pros and cons to both, but I know which one I would want in charge of a dangerous system, So, they do exist. It's just a matter of making sure that the right model is used when you're developing these AI softwares in charge of things like nuclear technology. Anyways, that's my fun fact for the morning. Any questions about that?
And also,
Yeah.
sorry, just to go to what you were saying.
Yeah.
The people that made Claude were the ones that deny that they want to go with the U.S. government,
Mm-hmm.
and that the U.S. government started making sanctions on them. So anybody that used Claude or any programming like that had to stop using it within 30 days. So that kind of affected
Yeah.
the sharehold and all that stuff.
Yeah. You say no to the U.S. government, and you are on the naughty list. Yeah, Claude, Anthropic was the company that denied giving their model to the U.S. government. To be fair, I believe the military approached them to use their model because of the specific imperative built into Claude not to hurt a human. They were going to adjust it to not hurt certain humans. But Anthropic denied that, and so they had to turn to someone else, and they are building that weaponized AI platform from the ground up because Anthropic wouldn't give them a base model of Claude. So they got a lot of sanctions on them, which was great. It's nice to have a vindictive government. It's not always vindictive, but it can be. Okay. Anything else? No? Should we get started? Great. All right. So today we're going over sedimentary environments. We talked about plate tectonics last time, right? And then you got your lab, which was all about stratigraphy. I did that for my in-person class. For my online class, because my recording stopped about 30% of the way through the lecture last week, I uploaded the copy of this lecture from a year and a half ago. So I don't remember in that particular class if I gave lab 2 during lecture 3 or during lecture 4 here. But all of the instructions for how to do lab 2 you'll find on either my YouTube channel or in the recording I uploaded last week, if it was there. And if not, there should be a lab 2 training video. I'm trying to remember to look for that and post it for you guys. But lab 2 is very straightforward, and we will talk a little bit about the concepts there. Stratigraphy is all about the study of the sequence of layers of rock to make an interpretation about the events that transpired to make those layers of rock where they were. Okay? The sequence of events that happened over geologic time, essentially. So you look at something like this. What are we looking at here? You're basically looking at one of the stratigraphic columns in real life. Right? You see that? This is actually fantastic. This is off the coast of Ireland, I want to say. This is like 200 million years or something like that of history that you're seeing in this column of rock. Like that, if I remember correctly. It's been a while since I looked up that. But you can also see these layers. These layers are doing some sort of funky interaction here, right? Does that look like anything we've seen in the past? Say it with words.
I don't remember the words.
Cross bedding. Look at this working together. We got the cross, we got the bedding. Good job. Okay, cross bedding. Good job. It does kind of look like that. That's not what it is. I'll tell you what that is here in a little bit, but it does kind of look like that. Okay, and then you can see the layers in these hills right here. This is Badlands. If you guys ever go out to North Dakota, South Dakota, Montana, even some places here in Texas, some places in Oregon, they have these places that are just commonly referred to as Badlands. Very, very dry, arid like this, very little running water, lots of hills that are weathering and breaking down. I've spent a lot of time in the Badlands of Montana and the Dakotas looking for dinosaur bones because it's really cool. A lot of these are layers of rock from the dinosaur time period, and the bones just kind of fall out of the hillside. It's really easy to find them. Well, easier than most other places where you have to dig down for them. Here they're exposed in the side of the hills, and you can just pull them out. It's pretty cool. All right, so our environments that we're going to talk about today, I'm going to break into 2 categories, marine and non-marine. Someone remind me what the word marine means. Huh? In the water? Is it just water, though? Is it all water? Oceanic water specifically. Okay? And this does include environments that include, organisms. We'll talk about all that. But marine specifically means ocean. Ocean environments. Okay? And then we have non-marine, which are non-ocean environments. That does include some water systems, rivers, lakes, etc. Okay? So, ocean basins, nearshore shelves, that includes, things like beaches and whatnot. Deltas, lagoons, those are all marine environments. Anything that has to do with being on land and not associated with the ocean, that's non-marine. So let's talk about marine environments first. Ocean basins. Ocean basins are the deepest parts of those oceans, okay? Way out there, far from your continental shelf. What grain size are we typically going to see out in a deep ocean basin? Why would it be small? Because of what? I mean, weathering's happening everywhere, sure, but why specifically would we only get fine-grained sediments out in the deep ocean?
Oh, because the pipe can't carry the heavy oil.
Yeah. You're okay. So what you were saying, you just kind of said, but you said high energy. It's low energy. Bingo. There is low energy in the deep water, and therefore only the smaller particles make it out there and sift down to the bottom. All of the heavier stuff gets left in the high energy areas closer to the coast, okay? So we don't get sandstones out in the middle of the ocean. We get siltstones. We get shales. But we also get the accumulation of a lot of tiny little organism shells. Plankton, zooplankton, all the tiny little plants and animals that live in the water. They live and they die in the water, and then their bodies go where? The bottom. Bottom of the ocean, and they collect there. Now, we call these collections of dead animal bodies at the bottom of the ocean, we call those ooze. It's an ooze. O-O-Z-E. It's an ooze. It's kind of a thick, slimy mass of dead microscopic animals down there at the bottom of the ocean. Now, when those oozes go through the process of lithification to become rock, they're going to make a couple of different types of rock based upon the composition of that ooze. We have a calcareous ooze, which forms from a lot of calcite-rich shells, and we have a siliceous ooze, which forms from the accumulation of a lot of silica-based shells. Do you remember the circumstances that would dictate whether or not we have silica shells or calcite shells? What dissolves in what temperatures? Yes, calcite is a weird outlier among minerals for a number of reasons, one of which is it dissolves easier in cold water. So our cold water organisms don't typically use a calcite-based shell. They have a silica-based shell. So if I'm looking at a layer of rock that is rich in what used to be a siliceous ooze, but has turned into something like chert or flint, if I'm looking at that and I see, oh, there's a lot of chert beds here, indicating an old siliceous ooze used to be here, what can I interpret about the environment at that location? It was cold. Yes. My animals in my water column would have used calcite if it was warm. Okay? So, and by that token, if I go and I look at this and I have layers of like limestone, right? If I have a lot of calcite in my rock, that's probably going to tell me it was a warmer environment. If I'm looking at it and I've got shales with beds of chert in it, that's indicating what used to be a siliceous ooze. It used to be silica, which means it was colder. Okay? So just a few observations for how we can interpret things like temperature just by looking at what's included in our rock. Some of the caves that I go into have these weird blobby shapes poking out of them. It's a limey shale or a limestone for some of these, but they have just blobs of chert poking out of them. When that can easily represent a transitional temperature environment, right? Where there was this influx of animals that use silica-based shells for a while, and they died, fell down to the bottom, became silica ooze, and then it went back to being warm again. And so the calcite shells stayed. And so I get these limestone beds with a bunch of silica nodules in them from these brief periods of colder temperatures. Okay, so I can, as I'm climbing through a cave, I can look at this in the different layers and I can interpret temperature variations in the past as I'm going deeper underground. Okay, the closer we get to the ocean, the larger our sediments will become. Why? More energy. Okay, so there are these things called tempestites, which are pretty neat. Tempestites, when I say tempestite, what do you think? What is a tempest? Huh? What is a tempest? Have you guys heard that word before? Something somewhere is what?
There's somewhere with, I don't know.
I'm guessing
A tempest is a storm. It's kind of an older style word. We don't really use the word tempest anymore, but it is a storm, okay? So a tempest is a storm. So a tempestite is going to be a type of rock, or a structure, I should say, in your rock made by the presence of a storm. How can a storm do that? Well, it has to do with storm wave base. Remember when we learned about shorelines? So here we go. Here's our water level right there. Okay, remember a wave is a column of energy that goes down to a certain depth. Below that, that energy doesn't have much of an effect and it doesn't do anything. But the bottommost part of that energy is wave base. It will encounter our shoreline right here. And at that point, when the energy runs into it, it will start picking up sediment and moving it inland. Okay? Normally, it's already close enough to shore that that's pretty much just sand. But when there's a storm, storms bring more what? More energy, and a heck of a lot more of it. Okay? So when we have a storm, we have what's called storm wave base, which is going to be deeper in the water. And it's going to start moving sediment from deeper in the water towards the shoreline. Now, when we get a very powerful storm, and its storm wave base is deep enough, it's going to start pulling up the already congealed, packed together, fine-grained sediments deeper in the water. And so we're going to get chunks of silts and clays ripped up from deeper in the ocean, carried inland, and deposited in the near-shore sediments. You can see that right here. Tempestites are characterized by these chunks of deep water siltstones and shales that got pulled up from deep water, pushed inland, and are deposited in these sandstone beds. So we have a near-shore sandstone with chunks of deep water sediment in it. And I would look at that and say, tempestite, and by looking at the sequence of tempestites in a layer of rock, I can determine what the general storm cycle was for the environment that far back in time. Neato. Okay. Deltas. You guys remember the deltas? We were talking about this. Can you remind me where this delta is? Anyone remember that? Huh? It is. Huh? Yes, this is the Mississippi River Delta. Where is that? Louisiana, yes, this is Louisiana. This is the current outlet for the Mississippi River, okay? This is the currently forming delta right there. This was the past delta, this was the delta before that. It's had a sequence of many, many deltas. About a dozen that we can easily see from aerial views, probably more than that going further back in time because they build on top of each other. How does a delta work? Well, you get a whole bunch of sediment moving downstream, especially in something as large as the Mississippi. Okay? It carries all that sediment downstream. It has energy. That energy has picked up the sediment and it's moving it and it's moving it and it's moving it until what has to happen for that sediment to stop moving? It loses the energy by running into something. What does it run into? The Gulf of Mexico. Yeah. An extension of the Atlantic Ocean. Okay? So it runs into the water here, loses all that energy, dumps that sediment out, and adds to the delta. So our deltas continually are being built outward further and further into the ocean. Okay? This is how they keep moving out. This is how these deltas continue to move further and further and further and further out into the ocean. Okay? So the section of our delta that's above water, we call that the delta plain. Then the section that is making the front, we call that the delta front for obvious reasons, okay? And then our prodelta is where the sediment is currently stretching out further into the ocean the furthest, okay? So delta plane, our river is dumping some sediment there. Delta front is dumping most of the sediment there. And then gravity is taking some of that and pushing it further downhill out into the pro-delta. And layer upon layer, it goes further and further out into the ocean. Now, the deeper the ocean, the further out you go, the deeper the ocean gets. So the further out your river is pushing, the longer it takes for that delta to go, okay? So it tends to slow down over time as it goes further and further out into the ocean. Okay. A lagoon is what forms when a barrier island is built up along your coastline. You remember what I was talking about with the storm wave base, right? Wave base and storm wave base just now with the tempestites. Well, that same thing is happening here, okay? Except instead of bringing the deeper stuff out, normal storm behavior or normal wave behavior is pushing sand up closer to the shoreline as it approaches the shoreline. Except what happens here is our sand starts to pile up in front of the shoreline. It doesn't make it all the way to the beach. It starts piling up before it can reach the beach. The higher that pile gets, the weaker the wave action that actually hits the beach is because the sand has made a wall. Okay? Gentlemen, we good? Okay. It starts making this wall of sand, okay? And your energy from your waves runs into that, and very little of it actually makes it to the beach. So our lagoons tend to be more calm, fine-grained environments, okay? Because less wave energy goes, and so less wave energy means less large grain sizes, okay? So if you ever go to Padre Island, right? If you ever take a vacation over to Corpus Christi or Galveston or out there, all of those islands along the edge of the Gulf of Mexico there, those are barrier islands. And behind them, that's the lagoon, okay? That's part of the big tourist draw. Very calm, fun water to go and have a variety of water sports in or fishing, whatever the case may be, okay? Now, how can we tell if this is a sedimentary structure that we observe in the stratigraphic layers? Well, the sequence of rocks, that's going to be our friend here. If we are observing the formation of a barrier island, then what we're going to see is sand and then lagoon sediments, so fine-grained sediments, and then sand again because our beach. Okay, so if I were to drill down right here and take a core sample, I would see sand, fine-grained lagoon sediments, sand for my barrier island. Kind of sandwiching it together. That's pretty indicative of a lagoon and barrier island situation. And then on top of that, I can also look at the fossils, because you know what? Lagoons, lots of very unique, specialized forms of life live in lagoons. Okay? You'll get different types of fish. You'll get different types of crinoids. You'll get things like stromatolites living in lagoons that can't live out in the open ocean. Okay? And on top of that, lagoons oftentimes are subject to more extremes when it comes to tide going in and out. Okay? So because we have these narrow inlets of water here, when the tide goes out, all that water gets sucked out, and then when the tide comes back in, refilled. Okay? So we'll see alternations in the depositional layers of the fine-grained sediments here based upon consistent low and high tide movements. Okay? Your organisms also adapt to that sort of constant influx and outflux of water in lagoons. All right, fossils are extremely helpful in helping us interpret sedimentary environments, okay? The ocean has a much, 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 much longer fossil record than land does. What does that tell you? Want to start here? There's been more quantity of life in the oceans, you're saying? Who's talking over here? I heard a voice over here. You can try.
There's more, I guess kind of like what they said, there's more life forms there that we can't analyze and study.
Could you
Yes. The fossil record for life in the oceans is much longer than the fossil record of life on land. What does that mean?
We haven't, wouldn't it make sense because since like, the ocean is a little bit like more unreachable, since we don't have like the technology to kind of look like for fossils there, that it's more preserved, so that's why like it takes longer, if that makes any sense. Since like for example like weathering can happen more.
You're talking about quality of preservation.
Yeah, wouldn't that make sense a little bit more?
So essentially what you're saying is land is more dynamic and therefore the fossil record in the ocean tends to be more preserved?
Yeah.
That might be true, except most of the fossils that we find from the ocean are now on land, but they originated in rock that was in the ocean. If the fossil record for life, that's what I'm looking for here, okay? We have far more fossils over time going further back in marine sediment than we do in non-marine sediment, insinuating very clearly life started in the ocean and then went to land. And this is something that we will explore the concept of later on in the class, okay? It's very, very obvious in the fossil record. The oldest fossils we have in the ocean are billions of years old. The oldest fossils we have on Earth are hundreds of millions of years old. Okay? So much, much, much more fossil record in the ocean. Yeah? You had a question? Yes, bacteria and archaea. Those are the two oldest types of fossils that we have. And again, how do you see it? Well, things like stromatolites, right, which we discussed last week. Those kind of mushroomy formations of mats of algae that built up, yeah? So you'll get actual sedimentary structures as a result of the existence of those things. There's also chemical remains, right? Nothing living, how do I put this? Everything living, very easy. Everything poops. Every living thing on our planet leaves behind some kind of waste, chemical residue, okay? Bacteria included. So the types of fossils that we can find aren't just physical things I can pick up with my hand. They are also chemical remains as well. Evidence. Classic example. You all know later last year when we got pictures back from the Perseverance rover on Mars, and it sent back the picture of those kind of mineral formations that here on Earth only occur because of bacterial activity. We're not sure if that's true on Mars. We're hoping to explore that as an opportunity there. But it points even more likely to a more likely scenario that there was at one point bacterial life on Mars. Not proof, just helps with the hypothesis there. That sort of thing, that sort of mineral residue left behind by the presence of bacterial life. Evidence of life without being a fossil. We would call that a trace fossil, right? So things like that. So we don't necessarily need hard fossils I can hold in my hand to know that something lived, right? Good question. Good questions all. Okay. So, but fossils are extremely helpful for discerning, for interpreting these sedimentary environments. There are these things called atolls. Have you heard of an atoll? An atoll is what happens when a volcano forms out in the ocean. Now, all we have right now is a volcano poking out of the ocean water, okay? But there's a lot more volcano under the ocean water. What likes to grow on land, close enough to the surface of the ocean, not on land, but on a hard surface, in the ocean, but close enough to the surface of the ocean to get sunlight for photosynthesis? Well, algae, yes, but reefs, right? And there have been algae reefs in Earth's history. You're absolutely right there, okay? We haven't gotten to that part. You're skipping ahead, okay? But we've got reefs that are made out of algae. We've had reefs made out of sponges. We'd have reefs made out of coral. We've had reefs made out of all sorts of different corals, okay? Bryozoans. All of these things require photosynthesis. Whatever the organism is that's making your reef, it needs to be near the surface of the ocean. So it needs to have an anchor on something that's near the surface of the ocean. And this volcano makes a perfect environment for that. And so you start getting this buildup of reefs around the edge of your volcano. Now, as weathering is going on, your volcano dies, it starts breaking down, its sediment gets carried away. That reef system just keeps on growing around it. So eventually, I'm going to end up with a volcano that's really not even there anymore, but this reef system that surrounds where it used to be. We call that an atoll, and at the center is a lagoon. This is a picture of an atoll today. Okay, this is a real atoll right now. Okay, that's an actual picture. So you can see the reef system that built up around where the volcano used to be. The volcano's not there anymore. It's actually kind of a deep, dark, scary-looking pit in the middle there. Yeah, that gets pretty deep. Why? Because this reef is stopping ocean sediment from washing in there. It is deeper than the area around it. That's all pretty shallow. That's all pretty shallow. Why? The reef has stopped sediment from going too deep in there. And so it is deeper than the area around it, which is why it's that darker color. Okay?
Have you ever dived anywhere?
No, I'd love to dive in an atoll sometime. My father was 23 years in the Navy. He spent 6 months stationed on an atoll called Diego Garcia. Naval base. The only way to get access to that island is to be in the Navy. But yeah, it's built on an atoll just like this. And he sent me all sorts of pictures. They were really cool, but I've never been able to dive in one myself. Yeah. However, these things have been occurring for as long as there have been organisms capable of building reef systems, which is hundreds of millions of years. Okay, so they are all over our fossil system, all over our fossil record, I should say. As a matter of fact, there is a gigantic fossilized atoll not far from us, up here, right there. We are hanging out right about here. You can drive to this thing today, and look, you wouldn't be able to see it. It's not sticking up out of the ground or anything, or at least not too much of it. But we know by looking at the fossil record and by looking at the layers of rock that it exists there. And look at how massive that atoll was. And then try and imagine how big the volcano it built around must have been. It's big stuff, right? Earth history is fascinating. Yeah, reef systems. Yes. I'm sorry, what? I couldn't tell you what city's up there. I'm not a Texas native. I can't just look at a Texas map and say, oh, it's by this place. Besides, that's a very large area of Texas. It's probably by a dozen cities. North of us, south of Lubbock. That's what I can tell you. Okay. You know what's a very fascinating thought, by the way? Have you guys ever gone to my office and read the little science cartoons I have on the door? No? Okay. One of them, so there's two stick figures, okay? And they're just kind of talking, and then all of a sudden, blip, there appears this like, kind of like energy dot or whatever, and it starts talking to them. It's like, hello, I am a human from 2 million years in the future, and I have come back in time to collect samples of these mysterious creatures called spiders. Because we don't have any then. They're all extinct, and we want to learn more about them. That we don't really have much of a fossil record for them. And the people are like, whoa, you don't have spiders? That's crazy. Sure, yeah, we'll help you find some spiders. Well, I'm paraphrasing, right? Turning it into a story format from a comic book, or from a comic strip. But he's like, yeah, we'll help you get spiders. Do you want some webs? I'm like, what's a spider web? And then two people just stop, and they think, whoa, spider webs don't fossilize. If they don't have spiders, they would have no idea that these animals made webs. And then they think even more, and they're like, dinosaurs are probably way weirder than we think they are. So in 2 million years, in the future, with no concept of a living spider, would have no idea that they make webs. How can we possibly know anything about dinosaurs other than what their bones look like, right? It's fascinating to think about stuff like that.
Do you think that dinosaurs look like how we think they do, or like?
So we can be pretty confident in a few things. Skeletal structure sets a pattern. right? And by studying living things and the ways that muscles attach in living things today, and the way that brains work, and the way that veins and arteries work, and the way that immune systems work, and nervous systems, and spinal cords, and all of that, the ways that those work today came from the things that lived before, right? So by looking at the way that things work now and the skeletal structure of things that work now, we make interpretations for things in the past. It's that aspect of the principle of uniformitarianism, right? Physical, chemical, and biological laws that operate today also operated in the geologic past. So this is us using things today to interpret things back then. But that doesn't leave room for us to know anything, like spider webs. There is absolutely nothing in the biological or the hard substance that would be left over from a spider, the husk of a spider that could be fossilized to indicate that they make webs. So what cool biological systems did dinosaurs have that didn't get fossilized that we have no idea about? So yeah, we're pretty confident in knowing what dinosaurs looked like skeletally. But then any more than that, other than the skeletons and the ways that muscles attach through the body, and things like head crests that we find the occasional fossils for, and we've even found a few skin impressions from dinosaurs that we were able to recreate some skin from, and even some feathers on dinosaurs, right? Other than those things, we have absolutely no clue, and it's all artists making things up otherwise. It's fascinating to think what we don't know. We don't know what we don't know about dinosaurs or anything else that lived on this planet before, other than what's been left behind.
Do you think they had like fur? Like they were like all...
Fur? No, we've never found any evidence that dinosaurs had fur. But feathers, yes. If you look at dinosaur toys, like a T-Rex toy from the 90s, it's going to look like a lizard on two legs, right? If you look at a T-Rex toy today, almost all of them have feathers. And the reason why is because we found fossils of carnivorous dinosaurs with feathers from before the time period when the dinosaurs like T-Rex came around. We have birds today. Birds are dinosaurs. Okay, they are the only type of dinosaurs that survived the extinction. Okay, we'll talk about this concept more later on. But birds are a type of dinosaur. They belong to the group avian dinosaurs that took to the skies instead of staying on the ground. Okay, so if there are birds, aka dinosaurs, today with feathers, and we have fossil evidence for dinosaurs 200 million years ago with feathers, what's the natural logical conclusion? Dinosaurs in the middle had feathers too. If you have feathers at point A and feathers at point C, you have to assume that there were feathers at point B too. And so that's why you see all of the different artist renderings and the toys and stuff have feathers now. Where in the 90s, when I was a kid, no one had any idea that that could even be a thing, right? All because we found these fossils of dinosaurs with feathers from that long ago since then, since I was a kid.
What about like things like fat,
Fat?
Yeah,
Like subcutaneous fat?
their chunkiness and
Their chunkiness. Reptiles today do build up fat. I have to be very careful with what I feed my lizards and my tortoises and my frogs because they will get fat. They will build up. They can get obese if you feed them too much fatty food. I'm having a fight right now with my box turtle. He doesn't want to eat his vegetables. He just wants to eat worms. And I'm like, tough luck, dude. I'm giving you sweet potatoes. And he won't touch those, but I'm not going to feed him any more worms until he eats some of his sweet potatoes. I don't want him getting fat, right? You're laughing at me. But yeah, it's reptiles do build up fat. They don't have the same capacity to build up fat that mammals do, simply because of the different metabolisms, right? They are cold-blooded. We are warm-blooded. We are naturally inclined to store energy for later use. Their metabolism relies upon an outside source of energy to burn that stored fuel, more or less. They can't just access it whenever they want. They still need to heat their bodies up to metabolize. Okay, so they don't build up as much as quickly as we do, but they still can. Could dinosaurs? Don't know. That's a thing that we can only hypothesize about. Yeah.
Going back to the spider web
Mm-hmm.
Like, wouldn't you know that from like a nervous system or something like that, or not at all?
Spiderweb organs are not tied into the nervous system, and nervous systems don't fossilize. They are soft tissues. Spinal cords don't really ever fossilize. What we do have are things like backbones. Anything that had a backbone had a spinal cord because the backbone evolved to protect the spinal cord. And being able to do things like walk upright was a byproduct of that. Spinal cord came first, backbone came later. Good questions. Anything else? Okay. All right. Continuing with our talk about marine ecosystem or marine environments here. When you have a shallow, warm sea, you get a buildup of calcite crystals forming out of the water, precipitating. Remember the process by which calcite forms in the water. Camera, stay with me now. Okay. The process by which these calcite crystals form in the water is your water warms up. Calcite tends to form a solid in warmer temperatures. It dissolves easier in colder temperatures. And so you get tiny little microscopic bits and pieces of calcite that fall down to the bottom of your warm shallow sea. Well, this builds up over time, making what we call a carbonate platform. Okay? So it's just a whole bunch of calcite crystals built up on the bottom of your ocean, and that makes your water very, very shallow, which, because it's shallow, means that it can remain warm. Deeper water can hold more energy, and therefore the sun doesn't heat it up as much. Shallow water, I mean, we're all familiar with this in the pool, right? The shallow end is warmer than the deep end, right? Shallow water stays warmer longer, or warms up easier, I should say. And so when you look at a map, a depth map of, say, here's the Bahamas, okay? Here's the edge of Florida, here's Cuba, here are the Bahamas right here. Anywhere you see that's white, that's between 0 and 500 feet. Look at all of these carbonate platforms built up around the edge of the Bahamas. And around that, it drops down to 5,000 feet. And then out here, 10,000 feet. But over here, where all of this calcite has precipitated, it's much shallower. We call that a carbonate platform. It is that shallow because of the amount of calcite, aka carbonate material that's built up there. And that's a combination of the precipitation of calcite from the water and the dead things that fall down into that water column as well. And then stromatolites. Stromatolites are the fossil structures, the sedimentary structures left behind by the alternating layers of algae and sediment, and algae and sediment as the tide comes in and out in these lagoons. Okay, it also happens on carbonate platforms. We see less of these on carbonate platforms these days. Most of the time, stromatolites remain in very salty lagoons and tidal flats, for reasons we will talk about later on in the term. But I'll just tell you right now. Stromatolites were one of the earliest sedimentary structures associated with life. They've been around for billions of years. That means that everything came later, thought they looked real yummy, and they made the bottom of the food chain. So we don't see stromatolites out in the open ocean anymore because stuff would eat them. Instead, they stay in super salty tidal flats. So they're not always in the ocean, and therefore the things that are in the ocean that would eat them don't get to eat them all the time. Or they're in very salty water, which is hostile to the things that would want to eat them. That's pretty much where we see them these days. Any questions about marine environments? All right, let's move on to non-marine environments. Starting off with soil. Soil is a combination of 4 things: water, air, mineral content, and organic content. Okay? That organic content we call humus. Yeah, humus. My kids and I planted their first ever garden 2 weeks ago. They are growing carrots, strawberries, and marigolds. What we planted that garden in is a prepared soil that I got in a bag from Walmart. Okay, when I popped it open, it had a whole bunch of dirt, a whole bunch of mulch. Okay, so it's a whole bunch of like ground up sticks and leaves and stuff. Why does it need all of that? Because as time goes on, that stuff weathers and breaks down and becomes that nice, yummy organic content that the plants need to survive. Okay. The dirt, that's the organic content. We water them every day, right? We're keeping up with the soil, but it needed that organic content to begin with for those plants to survive, okay? The parent material that my mineral content comes from is the primary factor in determining what the chemistry of my soil is going to be, okay? So if I have a soil where the mineral content comes from, say, granite, I'm going to have very different chemistry in that soil than one that comes from soil that comes from, say, siltstone, okay? Very, very different sources lead to very, very different chemistries, which will allow very, very different things to grow in that soil. Maybe one soil is naturally more acidic. Maybe one is naturally higher in silica. Maybe one is naturally higher in calcite, right? Different minerals will grow differently in different areas, which is why we don't see mangrove trees out here and why you wouldn't find a cactus in the Amazon, okay? As time goes on, that soil is going to change. What's going to change that soil? What factors might influence that soil over time? Weathering for sure, because my mineral content is going to keep breaking down, right? What else?
We have a sediment here, you move it to over here, it's going to change this composition here.
Right, so the erosion, okay? Weathering is going to be doing that as it moves, though. Erosion is the transportation, weathering is the change, right? They're often happening simultaneously. But what else? Is there anything...
The minerals, no, not the minerals, the life, like the ecosystem around it.
Yes. Yes, absolutely. Whatever life is utilizing that soil is going to change it. Plants are going to be pulling things out of that soil to survive and grow. But you know what? They're also putting stuff back in. They're changing it that way. A plant dies, it adds its own organic content to that soil. Some plants naturally remove gases from the atmosphere and put them back in the soil. Right? Yeah.
Does the soil get like harnessed because of that? Or like...
It depends to what degree it happens. There are plants that are called nitrogen fixers. Okay? They essentially remove nitrogen from an atmosphere and then put it in the soil. Okay? It's not necessarily bad for the soil, and as a matter of fact, there are plants that rely on pulling nitrogen out of the soil to survive themselves. Those are often naturally complementary to each other as a crop to grow, where you have one that wants nitrogen and one that puts nitrogen in the soil, and they complement each other that way, so you can always grow one or the other as long as you are constantly cycling between the two.
That's what they do in agriculture.
Yes, yes, called crop rotation. So you'll grow soybeans one season and buckwheat the next. I don't know if it's exactly those two. I know that those two are both in crop rotations. But beans and corn are another common example. Yeah, alfalfa, right? Those are all crop rotation, rotating crops. All right. When you cut down into the soil, you'll find that there are a variety of layers. A nice, normal, kind of middle of the road, I don't know, like you go up into Oklahoma and you slice down through that soil, you're going to see something like this. Usually you'll have a very narrow O horizon, which is just organic matter that's decaying on the upper surface. Then you'll have your A horizon, which is topsoil, a nice mix of all of the four factors. Then you have your E horizon, zone of leaching, which is going to be mostly mineral content. Then your B horizon, which is all the clays that don't get used up there end up getting deposited down here. And then underneath of that is your bedrock, which is actively breaking down, in the process of breaking down. Okay? Different horizons will be thick to different degrees based upon where you are. Your environment is a huge factor in determining what type of soil you have. Here, we have like no O, very little A, mostly E and B at the surface. Okay? Why? Because where we live 100 years ago now was subjected to something called the Dust Bowl. Most of our topsoil blew away. Okay? As was most of the other area around us. But you go to a place like, I don't know, Alberta, and they're going to have very different soil from us. Same with the Amazon, same with the Antarctic, same with Romania, right? All of these places are going to have different thicknesses of these layers dependent upon what the environment is like at that location. Moving on to our brief overview of glacial activity. How glacial activity can make sedimentary structures. Glaciers move slow, sure, but they are incredibly powerful. And so they will pick up things and carry them hundreds and hundreds, even thousands of miles at a time before dropping them somewhere. When a chunk of rock is picked up and dropped somewhere far away, we call that plucking. And what's left behind is a glacial erratic, like this giant boulder of granite here, sitting out here in this field, where it has no business being, deposited there by a glacier. Okay? That is a glacial erratic. That is a structure when it gets incorporated into the sedimentary environment, or the sedimentary layers later on. Abrasion is what happens when our glacier scrapes over a rocky surface and leaves giant grooves in it. Now, what happens later on if this glacier is gone and then a river runs through here and deposits a whole bunch of sediment on top? Or maybe it gets really windy and dry and sediment gets blown on top of this. Eventually, all of that's going to get buried and go through lithification, leaving behind this surface that had glacial abrasion on it and is now preserved in layers of sedimentary rock. Okay, so those are features that we will find in sedimentary layers. Glacial valleys are very large sedimentary environments, very wide. We describe them as U-shaped valleys, okay? The glacier has scraped it on every side wider and wider and wider. The U just keeps growing outward, okay? Feeding into each one of those are these cirques, C-I-R-Q-U-E-S, okay? Those cirques feed the ice into this glacier as it moves downhill, making a larger and larger glacier. And glacial valleys, once our glacier is melted, glacial valleys are often filled with river systems unless they're near sea level. Do you remember what we call it when a glacial valley is near sea level and then sea level rises? It's a fjord, exactly. Why would sea level rise as ice is melting?
It's an accumulation of like the rain and stuff, so if you're not feeding it back down into the ocean, or vice versa. If it starts melting, you're going to fill up the ocean more.
As it starts melting, you're going to fill up the ocean more. Why?
Water being added to the ocean.
More water is being added to the ocean. That, right? Okay. Yeah. The more water on Earth is bound up in ice, the less water there is in the ocean. So, if I melt all that ice, that water is going to go into the ocean as sea level rises. Therefore, any glaciers that have carved their way all the way to sea level are going to leave behind a U-shaped valley at sea level. But that's sea level during that ice age. When the ice age ends and all that ice melts and it goes into the ocean and sea level rises 20, 30, 40, 60, 100 feet, it's going to fill in that glacial valley. And that's what makes a fjord. Arêtes are the ridges between each one of these cirques, or glacial valleys. And horns are where multiple arêtes come together and make a very sharp peak. Roches montagnaises, these are things that we don't typically find preserved as a structure in layers of rock, but we do see them on the surface in places where there was a lot of glacial activity. It's where a hill kind of got kind of run over by a glacier and flattened out on one side into this gentle slope, and it has this steep slope on the other side. Same physics at play here, by the way, is what makes a dune. Remember how a dune forms? Your gentle side is where the wind is coming from, and it's blowing sand up that side at a gentle angle, and then gravity pushes it down the other side. The same physics are at play here to make this roche montagnais, except it's with ice instead of wind. Glacial drift, or glacial till, is the sediment left behind by glacial activity. It makes, when it gets compacted together, it makes this rock called tillite, which you saw in 1403. It looked kind of like sandstone or conglomerate, except all of the fragments were very jagged, very sharp. There wasn't really any cement to speak of. Just kind of shattered rock is what it looked like. And for reasons, it's because it was completely, utterly pulverized by the action of that glacier. Something else that it leaves behind is called rock flour. That rock flour is extremely fine-grained sediment from the pulverizing action of that glacier. And the thickness of that rock flour deposit tells us how intense the melting seasons were for that glacier through time. Moraines are how that sediment moves downhill. So before we can have a buildup of tillite or a buildup of rock flour at the bottom of my glacier, it needs to get there somehow. How does it go from point A to point B? On the glacier. This glacier is essentially a conveyor belt of ice moving downhill. So if anything else is on that ice, it gets carried downhill as well. So as rock is getting scraped off the edge of the valleys and onto this glacier or in the glacier, it's getting carried downhill via these moraines, where it gets dumped there. And this can make sedimentary structures, which you've actually seen. Do you guys remember when we were learning about shorelines, and we looked at the Cape Cod on the edge of Massachusetts? Yeah. I told you that the core of that structure is a glacial moraine. We wouldn't know that without an understanding of how moraines work and the technology to drill down and see such things, okay? But that is a sedimentary structure from a glacier that then influenced the creation of a sedimentary structure on a shoreline, the barrier islands there, and that spit of Cape Cod, that peninsula that comes out. Any questions? All right. Deserts then. Quick recap on deserts. They are formed mostly through air currents that contain warmer or cooler or hotter or drier air, okay, circulating around in our atmosphere. At the equator, things are hot, right? Why are things hot at the equator? The most out point of the Earth. What do you mean?
Like it's closer to the sun.
Closer to the sun?
The core?
It's because of its tilt.
Because of its tilt.
The axis.
Is it closer to the sun, or is it more exposed to it? Is that what you're saying? Got it. You know what's interesting, though? You weren't actually wrong with your first statement. You said it's out more. I'm not sure if this is what you meant.
Yeah, yeah.
Do you guys know that our beautiful blue marble sphere here is not a true sphere? Because we are spinning, at an angle, Earth bows out a little bit like that at the equator. The equator is actually about 20 miles stretched out around the edge of our planet. Yeah, you knew that? Cool, cool, cool. It's out more, guys. That's what he said. It's out more, right? So, that's true, but that doesn't have, that's not the reason why it's hotter there. It's true facts, but not the reason I'm looking for. No. It's warmer here because of the cross-section of atmosphere that the sun's radiation has to get through. So let me redraw this, and I'm going to draw it as a perfect sphere, even though we just established that, it's not, right? So if this is the surface of our planet, and then I'm going to exaggerate this a little bit, but let's say this is our atmosphere, okay? That's our atmosphere above our planet, the outer edge of our atmosphere. The sun is over here, right? And it is beaming radiation at every edge, at every surface of our planet. Now, that radiation at the equator, which is always pointed directly at the sun, has to get through this cross-section of atmosphere to reach the surface. But here, further from the equator, it has to get through, more cross-section. So if we say this cross-section is 1 atmospheric thickness, up here it might be 1.2. Down here it might be 1.4, right? Depending on how far from the equator you are. So by the time we're talking about the poles here, if I were to continue this sphere that way, and our atmosphere, by the time this radiation reaches a pole, it has to go through that much cross-section of atmosphere to reach the surface. Yeah. Atmosphere does what to that radiation? Is there some refraction? Absorption? Radiation is energy. The gases in our atmosphere absorb some of that energy, so by the time it reaches the surface, there is less of it, which is why we get cold poles and a hot equator. Cross-section of atmosphere. Okay? So, now that we've established why the equator has the hottest temperatures, typically, right? Well, consistently, I will say. Hottest temperatures typically occur in deserty sort of areas. But so do the coldest temperatures as well. Slight tangent. Why would we, in a desert, there are 2 ways that you're going to die. During the day, you'll die from heat stroke and dehydration. During the day, or during the night, you'll freeze. You guys notice that? It gets really hot and really cold in deserts. Why? It absorbs the heat very quickly and it releases it very quickly. But you said, what was the first thing you said?
That there's not like enough shade or like environment. I forgot what he said.
Shade makes no difference to a desert. When I say desert, what's the first thing that comes to your mind? Huh? Okay, sure, the Sahara. Water. A river would not make a difference, but you know what would? Water in the air. Humidity. Do you know what the most common greenhouse gas on our planet is? Water vapor, actually. Water vapor is a greenhouse gas. Cancel it. Right? Greenhouse gas is bad. Isn't that what social media is telling us? Right? Greenhouse gases are bad. Water vapor is the most common greenhouse gas. It restricts, and absorbs energy. Right? More greenhouse gases in our atmosphere, the hotter things get. But also, the less extremes, typically. So in a desert where there is very little water vapor, humidity is very low, Sure, your surface is going to absorb a lot of that energy quickly, but it's also going to release it quickly. And because there are so few greenhouse gases in the atmosphere at this desert, to retain that energy, the energy is lost, and your deserts get real cold at night. Okay? So just a quick explanation of that phenomenon. Okay, so back to this. Equators. Lots of humidity from evaporating water. Therefore, a lot of heat retention. More consistently higher temperatures, okay? A lot of humidity means a lot of rain. A lot of rain here at the equator. But as that air, by forces of convection, is getting pushed up into the atmosphere, raining all of that water out here at the equator or near the equator and getting shoved north or south, it's getting colder and drier the further it goes because it's raining out all its moisture. So by the time it reaches these subtropical highs on either side of the equator, it reaches land again and is cold and dry, and that's where we will start to see those deserts form because of the lack of humidity. Okay? All right. Other places and reasons why we can see deserts. Interior deserts form because they are so far from any water source that they do not receive evaporation and therefore humidity. And you get that effect that we were just talking about, where you have those temperature extremes and your deserts form. Okay, the Gobi Desert is an example of that. Then you have rain shadow deserts, like the Atacama Desert here, where the prevailing wind direction goes east to west, and it's on the western side of the Andes mountain range. So the wind carrying all the evaporated water from the Atlantic here is going this way, running into the Andes, climbing over the Andes, cooling off the higher it gets in the atmosphere, raining out all that moisture on this side into the Amazon rainforest, and only cool, dry air makes it over the Andes and into what becomes the Atacama Desert. So even though there's an ocean right there, none of the evaporation from that ocean is taken over here because the wind directions go east to west. In desert environments, we see removal of sediment. Okay? The removal of sediments is called deflation because what's happening as time goes on and sediments are removed away, your ground level kind of slowly starts to recede like this. Okay? Leaving behind the larger particles that could not be carried away by the wind, which makes something called a desert pavement. So you'll get all of these larger rocks left behind in an older desert where the younger sediment, or not the younger, the smaller sediments like the sands and silts and such got carried further away. A ventifact is a structure left behind when your wind has sand-blasted an object based upon wind direction. So usually it'll take on an aerodynamic shape like this one. Kind of looks like an arrowhead. Why do arrowheads have the shape that they do? Because it's aerodynamic. They fly through the air more efficiently that way, right? People have known that for thousands of years. This formed this natural aerodynamic shape. No one made it like that because of the effect of wind sandblasting this with all of these particles around it over time. This yardang was formed through a similar process. Do you remember when I explained how these form? You remember I drew you the cross-section of an airplane wing? Yeah? Good. I don't need to go over that again. But essentially, this has the same cross-section of an airplane wing because it is aerodynamic based on the direction of wind. Which way was the wind coming in this picture? Do you remember? Yeah, it's going left to right here. How do we know that? The shape of this is aerodynamic in that direction. But also, look at the edge of the column here. There has been far more weathering down here at the base on this side than there has been on that side. Right? So that's how, those are two clues that we can look at this to know what direction the wind was blowing. Okay? Sand dunes are formed through the passage of wind carrying sediment and dumping it in a hill shape. What happens is there's only so much energy that can push a sand so far. So it's not going to go from point A to point B all at once, or very rarely will it. It'll go here and then stop, and then here and then stop, and then here, and it'll tumble and it'll tumble and it'll tumble. It'll take a while to go from A to B. So we get these hills of sand forming as this process is occurring. The sand goes up the hill, tumbles down the other side. So we have our slope and our slip face on these sand dunes, as we call it. Okay? And that's why those form. The wind is slowly pushing it up the hill, and then gravity is quickly forcing it down the other side, making your slope and your slip face. Well, that is what happens to our sand. What happens to our silts and clays is they tend to get carried pretty far. They can even make it across the Atlantic Ocean. As you can see here, Saharan silt and clay getting blown all the way across to Central America. Okay? There are days over there where the air quality is so bad they have to wear masks because of the Saharan dust blowing across the ocean. Okay. While it is very good for growing plants, that's not particularly helpful when it's also invading your lungs. So it's more of a problem than it is a benefit for the folks over here in Central America. Prevent that dust from blowing? Didn't Pocahontas sing a song about stopping the wind and how you can't? I feel like that was some aspect of a song in the old Disney movie Pocahontas. But no, you can't stop the wind.
No, I know you can't stop the wind, but like you can't put like a border or something, or like something to stop the silts from traveling them.
Border walls don't stop everything.
What about like plants? Like growing tall plants?
Okay, so that helps in some places. So yeah, that's called a windbreak, and that will help stop the removal of sediment from a local area, like a small area, like your farm. But you can't like put a line of trees around the entire western edge of the Sahara Desert, or put one across the entire eastern edge of Central America to stop it from, getting in.
What about both? Stopping.
If you want to plant trees in the Sahara, I am behind you. You just gotta. I won't pay for it. You gotta find. you gotta find some way to pay for it. I'm gonna make sure that this. My PowerPoint froze there. I'm gonna make sure that this didn't stop. It did not, but it did zoom in for some reason. More. All right. I guess that's as far as it'll zoom out. Okay. Okay, so this is a video of how a meandering river carves through the landscape to make a river valley. Okay, so notice as it is spreading outward, it's going to go only so far before it abandons that stream and snaps back to the middle because it takes less energy to do that. Nature is always going to try and find the solution that takes the least amount of energy. It's not laziness, it's efficiency, right? Nature isn't lazy, but it does seek stability, and efficiency, that's a stable aspect, okay? So here we have our river valley that formed as a consequence of all of this moving out and snapping back and moving out and snapping back. Removing material, taking it downstream, depositing some of it on the way, but always removing more material than it deposits, okay? And that eventually is going to make it out to, the end of the river, probably out in the ocean, where it's going to make a delta, right? Braided rivers are not the opposite of a meandering river, but a meandering river is what we get in a very low angle area. right? The whole reason why that river has enough energy to move out away from its original course in the first place is because it's at a slope so gentle that gravity is not just forcing it to cut straight downhill. It's gentle slope, you get a meandering river. Steep slope, you get braided rivers. Braided rivers mean business. There's a little bit of deviation here, but that's mostly just to cut around various obstacles in their path. It's mostly carving a straight path down through this valley, downhill. Braided rivers have a lot of energy because of their steep slope, and so they bring lots of large particles with them. As a matter of fact, the most common sedimentary rocks associated with braided river environments, things like conglomerates, right? Large debris, large particles that go on to make those conglomerate rocks. Okay? So when I see deposits that indicate a braided stream or a braided river, I'm thinking very steep slope, probably a mountainous area. Lakes. Lakes can be a little tricky. There are lakes so large that sometimes they behave like mini ocean environments. They'll have waves. They won't really, there's a little bit of tidal action in larger waves or in larger lakes, but when the surface area of a lake is large enough that it has wave activity, you can start seeing things like beaches that look like shoreline beaches form there. So they can be a little confusing, but there are ways of telling if it's an ocean or if it's a marine or non-marine beach environment. Okay, looking at a lot of the local geology can help you see that. The fossils definitely help you see that. Okay, but when we see tiny, tiny little laminations, look how, this is a penny for scale, look how thin the layers of clay deposited in this are. We call these varves. Each varve is associated with a season of melting or freezing. Melting, let's say winter has come and I have dozens of feet of ice up in the mountains. Then spring rolls around, it starts to melt. That melt water is going to come down into my lake, bringing with it sediment. The thicker layers of sediment here indicate more melting because more sediment is coming downstream. Thinner layers, that usually indicates my periods of freezing. Thick layers melting, thin layers freezing. So I can look at these varves and see seasonal information here for that lake. Here's a larger example of that. You can see the different layers here, the thin purple layer and the thicker white layer. Melting and freezing seasons. Okay, different types of sediment and different thicknesses of sediment for each. Okay. Occasionally there will be some weird thing in my lake deposits, like if there's a cliff next to my lake and a rock falls off my cliff and into the lake, it'll get incorporated into the sediments there, and you'll find some weird stuff like this. This random big rock that's just stuck in the middle of this lake deposit. Look, you can see the varves below it. This clearly fell on top of the mud at the bottom of my lake, squishing those layers down. And then more varves deposited on top of it, right? Kind of its own weird kind of erratic there. So taking all of these factors, all of the things we know about sedimentary structures and sedimentary rocks here on Earth, we can interpret things about the past by seeing how they form now. I can see how dunes form now, layer upon layer, dune upon dune, and then by observing that interaction and seeing how those layers are deposited on top of each other, I can look at something like this and see the same thing. What do I see here? I see dunes on top of dunes, on top of dunes, on top of dunes. That's what this picture is. You are looking at preserved dune structures. You are looking at this 40 million years ago. Lithification. there are hundreds of layers of dunes underneath of this. And as more dunes are piled on top and you squish those dunes lower and lower and lower, the sediments get compacted. And even though the environment up here may change, that doesn't change what already happened and is permanently in the layers of rock below that. All right? So even if in 20 million years there's a rainforest on top of this, those dune structures are still down there. And eventually they turn into rock like this.
Is there a rainforest that grew on top of the dunes that we know today?
There was a large desert on top of where the Amazon is right now when it was part of Pangaea. There was an ocean on top of where the Sahara is right now. Environments change drastically given enough time, but the past environment is always preserved underneath of it. And this is where we make our interpretations from. This is where we gather all that information to learn more about our past. What you're looking at right here, my friends, is the principle of uniformitarianism. Physical, chemical, and biological laws that operate today also operated in the geologic past. What's the next part? What do I like to add after that? And will continue in the geologic future. We can look at what came before and after this to try and forecast maybe what might happen after that. What's the other part of the principle of uniformitarianism that I like so much, that I like to add? The physical, chemical, and biological laws that operate today also operate in the geologic past and will continue in the geologic future and are true everywhere else. What do you see here? I'm not asking where it is, not yet. I'm asking what you see. I even says a delta. Does anyone else see a delta? Dried up? Delta? Do you guys see a delta here? Do you see that delta? It is, in fact, a delta. Yes. This is a delta on Mars. Yeah. 2 billion years ago, Mars had running water on its surface. That's when this was made. Some time has passed since then, right? Look at that. That's an asteroid crater right there in the middle of our delta. The same geologic laws that make deltas here on Earth made this on Mars. If I can look at this and say the same processes happened here, all evidence points to the same processes happening on Mars as happen on Earth, why not everywhere else too? And that's where that last part of the principle of uniformitarianism that I like to say comes in. Those principles are true everywhere else until we have reason to think otherwise. Now, the Perseverance rover has been spending the last few years walking along, or rolling, I guess I should say, along the edge of this delta collecting samples. Because if there was ever life on Mars, it's going to be where the water was. Which, by the way, for there to be a delta here, we needed to have a river, which you can see the old riverbeds here, okay? But for deltas to form, that river has to run into something. What does the Mississippi River run into? An ocean. For this delta to form, not only did we need a river, we needed an ocean. We're still figuring out how much water was on Mars, but at least there was enough to have rivers and small oceans. Very well could have been life. There was life here. Okay? I'll leave you with that thought. Any questions? Okay. Well, then I'm going to end our lecture here and cut the recording. Please remember to come to our class prepared with questions for our final exam review. No, our exam 1 review on Wednesday. Online students, please get those questions to me no later than tomorrow night on Tuesday.